Hello there and welcome to episode 27 of Codebase Alpha. So here we are on a Monday evening here in the UK, afternoon wherever you are. So I hope you're enjoying your Monday. And so today we've got a slightly different stream than normal. So rather than doing more work on the AI chatbot today, we're going to be doing a bit of F#. And as my special guest today, hi Rambling Geek, welcome to the stream. As my special guest today, I've got Mårten, who you probably know better as Fuel Stable, who's a regular viewer in my stream and in many other streams, so you'll probably recognise him. And we're just going to pop over now into our pair programming stream, and I'll ask Mårten to introduce himself. So Mårten's joined us audio only, so he's represented by that Skype symbol that's over there on the left-hand side of the screen. So Mårten, would you like to say a few words to introduce yourself?
Hello there. Yeah. So my name is Mårten, and I'm living in Norway, and I'm very shy, so that's why I haven't. I'm not sharing my video. I don't want to be sort of turn people away from streaming. Yeah, I'm quite excited to have the chance here to come here and talk about F#, which I enjoy, and talk about parsers, which I also enjoy writing it. So let's see how these things work out, but I'm quite excited about this. I think it would be cool.
So Mårten, maybe you could is it Mårten or Mårten?
I say Mårten.
Mårten, okay. So I'll just pronounce it the English way. So Mårten, could you please perhaps just tell us exactly what a parser is?
Okay. So a parser is a way to. I'm sure we can find different definitions, but the way I will talk about it today is taking a string and turn that into an object tree.
Right.
So we are transforming. A simple way of a parser is taking a string and make it into an integer. For instance, but we can make more advanced things like taking an expression like 1 + 2 and turn that into an expression string. So the string is 1 + 2, and from that we can create a tree which describes that expression, and then we can compute that expression. So a parser is a way to sort of take a string and make that into some kind of tree structure, or a JSON object, for instance. Like we take a JSON string and turn it into a JSON DOM object.
Okay.
If that makes sense to you.
Yeah. Okay. That's interesting. So. Breaking down a string, you could do that in many different ways, but some would be kind of more difficult to actually achieve than others. What's the advantage that we're going to kind of derive from using a functional language like F# in doing that?
Yeah, so many developers, as you are reaching for regular expression when doing parsing.
That's right. Yeah.
And some people say they don't like regular expression, and it's very common not to like regular expression. I personally don't mind regular expression. I think that's a good tool for certain things. But regular expression is really used to sort of parse what's called regular grammars, which is a very simple way, which is a very simple way language, kind of. There's certain things that are very hard to express in regular expression, like parenthesis matching and operator precedence.
Right.
When you start trying to do that in regular expression, it gets very nasty, I think, quickly. In addition, regular expression has the drawback of not telling you why it failed.
Absolutely, yes. Yeah,
you're just saying it failed. And you go like, okay, what now? And regular expressions don't allow for sort of reusable, like say you define a /d+ to sort of represent digits, but then you can't reuse that pattern in different places in regular expression.
Right.
And finally, regular expression, you parse something using regular expression, but then you get groups of strings that you have to parse anyway. So the benefits in what I want to show today, we see how far we get, but if you use a parser framework like fparsec, it gives you all of that. It allows you to parse much more complex grammars. It's type safe in that the parser actually produces an actual value. It allows you to create reusable parsers that you can reuse in different places. And it's and finally, also, which I think is the most amazing thing about fparsec, is that also it gives you human readable error messages for free, which is, when I first saw that, was mind blowing to me.
Yeah.
How do they do that?
So that's a very good point. Michael Jolly, hello, welcome to the stream. Slayer Darth, welcome to the stream. So Slayer Darth just pointed out there was a bit of reverb on your voice there. I've just killed off the music channel on OBS, and I think that's better. So if anyone does have any issues with the audio for Mårten, could you let me know, please? Especially on the volumes, make sure that he's coming through at a sufficient volume. Okay, so Mårten, so we've got a basic F# program that's on the screen at the moment, which is the template, which when you create a console app in F#, we've kind of altered it slightly. So we put a different message in there. So if we do .NET run, we should see it come back saying hello Mårten from F#. Let's make sure that works.
I have a PR to Visual to F#, so that they should change this. In the default program is to say hello Mårten instead of hello world.
Yeah, absolutely. I think we should recommend that. We should actually put a PR into the repository for that.
Makes perfect sense to me.
Okay, so in a functional world, how do we actually start this task? What's the kind of basic building blocks we need to kind of build up so we can? So if our task is to, let's just put a comment in here. So our initial task is going to be to parse, and you're suggesting 1 + 2 as a kind of a simple starting point, which would be very hard to parse as in a regex expression. So what's the starting point in this? Because I've got to kind of admit that I last did in the F# about 6 months ago, and so I've forgotten a lot of it. So maybe you could kind of just start us off and say, well, how are we actually going to approach this problem?
Yeah. So what I want to show, in addition to doing parsers tonight, is also a little bit how maybe what's the difference between defining a functional framework compared to an object-oriented framework.
Right.
I think that could be interesting.
Yes.
We just to point out, we could also define this in C#, but I like F#, so let's do this in F#.
Absolutely, let's do something slightly different. And this is a pure, it's a pure functional language, isn't it? I mean, it has kind of got object-oriented features that because it's a .NET language, but it's very much a different type of language to C#, and it'd be interesting to see that.
But we will be very, I would think, say functional. So the way I want to start this thing is starting to think about what is and this is the difference thing perhaps between object-oriented programming. In object-oriented programming, maybe we think about the big picture. We start with the sort of, the interface on the big picture, and then we break it down further into smaller and smaller abstractions.
Right.
But often with functional programming, you start by what is the smallest composable unit, like an atom, that you cannot break apart any further.
Okay.
And start defining bindings, so sort of bind these atoms together into sort of molecules. That's the kind of picture I have in my head. So it's kind of the other way around in some sense. So I want to ask the question, how should this parser building block look like? And I'm going to write some code here now to have a suggestion here and see how that thing works out for you. And we can talk about these things. So I'm just going to suggest something, and we can discuss if this is what you think about this kind of parser. So I don't know how much you remember from F#, but what I said here is a parser is a function that, given a string, produces a value t.
Right, yeah. That
makes sense, I think, in many ways. So if you think about this, could be an int parser that takes a string and produces an integer.
Yes.
Or it takes a string and produces something else. But the problem with this parser is that if you want to parse 1 + 2, well, we probably have an int parser, and then we have a plus parser perhaps, and then and we want to put them together. And this thing, this thing parses an integer, but it cannot understand the plus sign. So this thing doesn't really compose.
Okay, right. See that.
So one way to do this is to say, well, take a string, return a value, and return the string that is unconsumed.
Like I said, break the string apart into its kind of, I guess, by some kind of delimiter.
So what I mean is, if we take the string, let's say we have the int parser.
Right.
So we apply this int parser on this expression. It consumes the 1, but it doesn't know what to do with the plus. So it will return the 1 number, the result, and +2 as a string that it didn't consume.
Okay, right, I get that.
So if you now that you write, and if you then we make this into a pair in F#. And the way we do it, we type the star. If you don't, I don't know how much you remember.
Okay, that like that. Oops, I'm in the wrong place.
Yeah, sure, no problem. Type star string.
So that's defined like a tuple, isn't it?
Yeah, that's a tuple or a pair.
Mm.
So this makes sense also, and it's more composable. But it's not perfect yet for us, because what happens when we write the parser is that the parser, we will have an int parser perhaps, and then we might also want to parse expressions like 8 + 2, 8 + 3 perhaps.
Yeah.
And how the parser typically works is, okay, we first try to parse an integer, but if that fails, let's try to parse a variable. And if that fails, we fail. So a parser can fail. And the only way for this parser to fail is to throw an exception.
Okay.
And I heard from your stream that you don't really like sort of having control flow by exceptions.
It does seem the wrong way. An exception should be an error condition which you can then either handle or hand off somewhere else, rather than using it for flow control. I must admit, don't like that.
I completely agree. And then we make this into a type that can sort of, we can sort of say we return a value when it's successful, or nothing when it fails.
Right, okay.
We have a type for that in F#. And that's called the option type.
Right, I remember the option type, yeah. So it's either some or none, isn't it? Something like that.
Yeah, some or none, exactly right. So then we add this thing here to a parenthesis, and we add option type here. Or we can add type right option. Yeah, I can type it.
Yeah.
Does that make sense?
Yes. Okay. So it's we're returning either the tuple of dash of tick t and the string, or we're going to return a non-value.
Yes. So if it succeeds, we get the value and the rest of the string, or nothing.
Yeah.
Now this thing we will be able to succeed with this definition, but for slight performance reasons, I'm gonna apply a little bit of sort of, because if we do this thing, we could do a lot of substringing, and substringing is inefficient.
Right.
And maybe we should use spans, but I don't really know how to use spans in F#. So I'm going to change this thing into a slightly different way. And now a parser means, and you stop me if you stop making sense.
Okay.
A parser means that given a string and giving the position in the string, so it points to some character into the parser, it returns the value and the new position in the string.
Okay, right. So int here is a position.
Yes. So when we start, the integer is 0, indicating the first character.
Right. And
when we start advancing through the string, the integer here will be incremented. And it's functionally the same thing as this substring we did before, but this way we don't have to create substrings all the time.
Right.
We just create a new integer, which is more efficient.
That's cheap, yes, rather than creating a whole new string object, yes.
Yes. And then a final thing, this will improve the signatures of the function. Did I get, no, I wrote, sorry, my bad. I'm just going to write this thing here to suggest that this is the final definition for us.
Okay, so what does the P of actually doing there? I've not seen that before.
This is a single unit, what's called single union case. And
Right.
why is it useful? Well, it's useful because if we didn't have that, the signature of the functions would not look like a parser. It would look like a function of this type, and that would make it hard to read the signatures of the types. Now, using this thing here, we wrap all of these things in a single.
Okay, I get what you're saying. So you're saying that it's going to return P, and we're defining P as being string to int to option of etc. Yeah. Okay, I understand that now.
But it's mostly a trick to get better sort of IntelliSense and these kind of things.
Right.
But we're ready to start now.
Okay.
To write our first parser. So now we're going to write. The first parser we're going to write is a parser that consumes a single character from the string. And if the string is empty, or at the last string, last item in the string, we're gonna fail because we cannot read something when it's empty.
Yeah.
But for all other cases, we're gonna return the character and advance the integer by 1.
Okay.
So just to start off, I'm gonna help you a little bit here.
If you would, please.
Yeah. So let's call this pchar, this parser of a character, and we say that this parser is parser of char. So the type of this parser, this pchar, is a parser that gives us a character.
Right.
And here I'm going to use this reverse shove, and this is a pattern that we see many times tonight. So what we're saying here is that we are constructing the parser using this P constructor, or this type. I don't know exactly the name. This case. This is taking what this does is it takes this is a function that given a string and an integer produces an option. Here's the string, and here's the position. If you can see my character,
I can see it, yeah.
And here is the position.
Yep.
Does that make sense?
Yeah. So you're saying defining this P, which is presumably this up here.
Exactly.
It's a function. It takes two arguments, one of which is a string, one of which is a position in the string.
Yes.
And it's going to return none.
In this case, but because this is just it. Now it will always fail. So I'm going to let you write some code now.
Okay.
So the first thing, this is much simpler than I think you believe it is.
Yeah, I'm sure it is.
The first thing, this is just an if the position is valid, i.e. it's less than length, it's somewhere inside the string. So we can start writing that if statement.
Yeah.
If I is less than s length.
Yeah.
Then what do we do? Now you need to type then in F#.
Then do you? Okay. And can I do it on the next line, like that?
Yeah, maybe.
Let's try it. Let's do it. We know it's going to work, and then okay.
And then you make a new line, or you don't have to make a new line, and then you indent it.
Yeah.
And what are we going to return here? Well, we're going to return some value, right? So you use the sum constructor.
Yeah.
And then you type a parenthesis, and the first value in this tuple is the character we are currently at.
Right. That's going to be
the string S.
Yeah. It's going to be in brackets, is it like this?
Yes, but in F# we have to write a dot between the brackets and S. No, not that.
Yeah. Dot. Yeah. Oops. And it's going to be I, isn't it there?
Exactly right.
Okay.
And then we're going to advance the position now. It's going to be advanced by 1 position because we consume this character.
Okay. And then Can we do it on the same line?
Yeah. You write that in the inside the parentheses.
Oh, okay. So I++, yeah. We do that?
Not there.
No.
If you remember the type definition,
I++.
the first,
yeah,
and a comma between the I.
Of course, because it's tuple.
Yeah, a tuple. And in F# you don't have I++. So you type I+1.
So I+1, okay.
Yeah. And now the thing is, now you're going to implement the else case.
Yeah.
And I will type that on a new line, but it's up to you.
Yeah.
And you have to unindent it. Yes, exactly right. And we just fail here, so that's none.
Okay.
And then finally remove the top none. So does this thing make sense for you?
It does. So it's basically what we're saying is we're going to pass in a string and a position. If that position is inside the string, then we're going to return whatever is at that position, and we're going to increment the position by 1. If it's outside the length of the string, we're going to return none. So that's our option set: some or none. Yes, that's coming back to me now.
And so what's cool here, to me, because one of the first things I did as a developer, not really first thing, but quite early in my career, I wrote an SVG parser.
Right.
Which sound like perhaps a bad idea, but that's what we did. And I wrote that parser, and I was disgusted by that code, because all over the code I was constantly testing: have I reached the end of the string? Have I reached the end of the string? And I felt the code was I couldn't reuse patterns. I couldn't write the code in a way that I did test one thing in one place. I had to spread this thing all over the code base.
Right.
I was really struggling. What's cool here is that if you do this properly, this is the only place where we will dereference the string. This is the only place we test against I is less than S length. In all other places now, we're going to build on this parser.
Right.
So no other parsers need to look at the string in this way. So we will encapsulate this pattern in a single place. And that was pretty cool.
That is really powerful, isn't it? So yeah, so it's more encapsulating than an object-oriented approach for it, isn't it? It's ultimately encapsulated, in fact.
This kind of sort of, the power maybe of function programming is the possibility to sort of, combine functions and using combinators. And that enables, I think, in some cases, better encapsulations.
Yeah.
So we are ready to run this parser now. We wrote an first parser. And so I think we should write a simple helper function that allows us to run parsers simply. So if you create a function called prun, perhaps, and then the first argument to this prun is a parser. And now I'm going to show you a trick that you might not be aware of, just for the fun of it. So if I borrow the cursor, we're going to deconstruct the parser directly in the command line, in the argument list. So by typing it like this, P, we are deconstructing this parser. So we get the function here directly.
Right.
So often we pattern match inside maybe a function, but we can actually do this inside the argument list in F#. So that's a little bit of a shortcut. And this is the string argument. So then we just run the P using the string.
So PS, yeah.
It's a small P.
Oops,
it takes big. God, why is that?
I don't know. Let me just override that. There we go.
Yeah. And you run the string.
Yeah.
And you pass the first position, which is 0.
Yeah.
And now we have something that can run this for us. So now we can run this parser. So if you go down in your in the main header link slumps, I saw there's a new guy here in the chat.
Hi, Linksubs. Welcome to the stream. Good to see you.
So let's parse this hello Mårten from F#, right?
Okay.
And what you do now is you type prun.
Yep.
And then you type pchar, which is the parser. And we're going to print this thing, so then you pipe this to printf. Printf and you use the percentage a.
Percentage A. There we go.
Now we can run this thing.
Let's do it.
See what happens. What do you think come out, by the way?
One would expect a H to come out.
Yes.
So we've got some H and position 1, which is the next character. Okay.
Exactly right. So let's try to provoke our parser and parse in an empty string. Because it shouldn't crash on that. That should work.
It should come back with none, shouldn't it? At that
yes.
point.
If we've done it correctly, that should be none. And it's null here, but it's not.
Yeah.
So a big success. This is the first. This is the first small step towards writing a parser. Now, what we want to do with parsers is that I'm a little bit unsure on the way to do this, but what we want to now we have a kind of an atom.
Yeah.
And we want to start building molecules of parsers. And I'm going to introduce you to some very silly functions now, which you think they almost do nothing. But they are going to help us build these molecules of parsers. So the first one I want to define is a function that's called preturn, for example.
So a new function up here, preturn.
Preturn. So the purpose of this parser will be, and it will take an argument v value, and the type of this parser will be parser colon parser. Parser and bracket t.
Tick t, is it?
Tick t, exactly right. Equals. So this parser we're going to make now, you're going to think this is silly parser, but it will turn out to be very useful for us. So this is a parser, so that means that we start with the same pattern, this p backward shove fun si.
I don't know why it wants to convert that into a capital, but we'll.
Yeah, but we'll copy paste. If you copy paste the line from line 9.
Yeah, there we go. So we're shoving back into there.
Yes, we are using live share here, Rambling Geek.
Yeah, we are live sharing, but Mårten's trying to get me to do a lot of the typing rather than him doing the typing. So it's I'm trying to kind of learn a lot of this as well. So it's slowly coming back to me, some of these things, some of the kind of functions and the ideas that Mårten's kind of talking about. But I'm very much, if you haven't done F# before, just ask questions in chat. Yeah. Thank you.
So what we want to achieve here is that this parser will always succeed with the value v.
Right.
So we're not going to look at the string. This parser is just going to, whatever we call this parser with, it's just going to succeed. So what we return when we succeed is some value, right?
Yep. So some v.
Yes. And the position. We need a position as well.
Yep. And the position is going to be.
Well, we haven't done anything, so let's just make it I.
Okay.
So now we find a very stupid parser, you think, but this is very, very useful. We can run it if you want to as well in the examples.
Yep, let's give it a go.
So if you add a new line here.
Yep.
prun, and then you type parentheses.
Yep.
And you return maybe SNB string, p return SNB.
Oh, p return.
Yes.
Yeah.
And then you send in an empty string as sort of the string to parse.
An empty string, yeah.
And not there, outside the parentheses.
Right. Yeah.
And then you pipe this to printf, the same printf thing as before. And now we run it and see what happens.
Right. I've got no idea what's going to happen here.
It's not going to be so exciting. But
let's give it a go.
And it returns some SNB.
Okay, so yeah, I don't understand the purpose of it, but
yeah, exactly right. What is the purpose of this function? It seems useless, but it's going to turn out to be quite useful. Now we're going to define its twin parser, which is we can call p fail.
Okay, so it's basically the same as this, but it's going to be a fail, yeah.
And this parser is always going to fail. And then you let it take the unit value or parentheses instead of v.
Right.
And then you return none.
So so here's going to be none, yeah.
Exactly. So this seems even more useless.
Yeah.
But we will see later that this is actually going to turn out to be quite good for us. Now we did some, okay, let's stop a little bit. But so they seem useless, but do they make sense? I mean, do you understand the code here?
Yes, I think I do. So this one is always, no matter what happens, it's always going to return whatever we pass into it. So p return is going to return whatever we pass into it, and actually it doesn't seem to matter what.
No, it doesn't.
It doesn't even take an I. It's like it just takes the value, and then it passes. It comes back with a sum option with our value in it, and then whatever I don't know where I is. So is this partial application going on here with this I?
The I is the position.
Yeah.
That we get passed in. So we don't change the position.
So it's always 0 then.
No. If we are further into the string,
right,
when we call p return. So
okay.
Say, this is called by another parser that we have already advanced. It can be not non-zero.
Okay, so it's the position we are when we actually when we call the p return function. It's whatever position we are in the string at that point.
Yes. Yes.
Okay.
And then p fail, it just fails.
Yeah.
So, but now, that was simple. So let's blow our minds a little bit instead and go the completely opposite direction of being simple. But this is one of the hardest things we write tonight. But it will enable us to do some pretty cool things. Because this will enable us to sort of start binding parsers together into more complex parsers,
right,
which we see will be very useful. So now we're going to define a function which I want to call pbind.
Oops, okay.
And you forgot the let, I think.
Yeah.
There was someone that tried to post a link here.
Was there?
Shirley Dev tried to post a link, I think. Oh, spamming caps, it said. And,
okay, never mind. Okay. Sorry, Surly Dev it was. Sorry, Surly Dev. We've got Nightbot kind of dialed up to the max here, so I will sort you out with a VIP badge after the stream, just so that Nightbot isn't so vicious with you. So welcome to the stream, Surly Dev. It's good to see you. So we're here with Mårten, and we're doing some F#. We're writing a parser, and Martin's blowing our mind at the moment with functions which don't seem to do a lot. So.
In 30 seconds, I think for most that are not used to functional programming, this is going to hurt a little bit.
Yeah.
But let's do it.
No pain, no gain.
Yes. So pbind will combine two parsers together.
Okay.
But we're going to complicate it a little bit. And the first argument to pbind the signature here actually will be identical to collect on a collection, and it has the same rules. But the first, I'm just going to tell you what the signature is.
Yeah,
here.
okay.
I can actually type it.
You type it, yeah.
Here. Wow, Rebel Geek, you're gonna, you might get some more brain hurt now. Okay. Shall we try to decompose this thing here?
Yeah, let's break it down into its bits, because it looks complicated.
Yeah.
But I'm sure we can understand it. So let's give it a go.
So the thing here is that we have a parser T. So this is a parser T that parses something. We don't know what yet. It could be a character, it could be an integer. And then we have a function that, given a value of T, returns a parser of U. And this should return a parser of U.
Okay.
I said before that this has conceptually is similar to select many. So let me type the signature for select many. We're not going to use this or collect, but let's call it select many from F sharp from
C sharp, yeah.
Yeah. It will look something like this. Now they're going to be red lines and whatnot, but I'm not going to care so much about that. Yes, this is VS Code with Ionide extensions. I think, at least.
So I'm using Visual Studio, and Mårten's using VS Code with Ionide. Yes, so it's kind of both, certainly, Dev. So we're live sharing at the moment.
So this is kind of the signature for select many, and you know what select many does. We have a number of T. We have a function that extracts an inner collection.
Yeah. So this is where you're flattening the structure of your.
Sometimes called flat map. Yeah. Sometimes called collect. This is kind of what we want to achieve here as well. It has the same structure, but parsers work a little bit different, but they have kind of a similar thing. So now, okay, so how would we, so what I would say here is, what's cool about function programming sometimes is that if you set when you define a good sort of, basic building block, the parser, or something that works, this kind of function actually writes itself.
Right, okay.
It's hard to believe, right?
Yeah, it is, yeah.
But this is a parser of T, and we are supposed to produce a parser of U, but we have a function that giving a T produces a U. So what do? Well, we need a T value, and the only way to get it is that we run this parser.
Okay. Oh, I now the light just came on. So this P run is basically going to do that, isn't it?
Kind of, but we are not going to use P run here because P run doesn't allow us to sort of specify the position.
Right. It doesn't know. That's correct.
No, but the P run is kind of the helper function to run the parser. When you have a full-blown parser, but we are inside the parser framework here, so now we're going to run this low level. But it's not so hard. So we're going to run the parser T using the argument SNI to get a value of T. And using a value of T, we then can get the parser of U. And the way we do it, it's quite simple. I'm going to type a little bit here. Right. So maybe talk a little bit here. So we have I run the parser of TSI. This is the parser. This is the string. Sorry, this I need to mark it. This is the parser.
Yeah.
This is the string, and this is the position we're at.
Okay, so that's understandable. It's just that I guess it's just the notation which, when you first look at it, it's quite confusing, but I understand. So all those values are actually represented within this p bind, aren't they? So here's the t, for example, which is the parser we're going to get.
Yes.
Here's the string we're passing in, because this is the function, and there's the position. So those are actually all represented by those TSI. Okay, fine.
And as you remember, this sometimes produces a none value.
Yeah.
We have nothing to do then. If this fails, everything fails. So then we just say,
we're going to return it on, yeah.
Okay, whatever. But if it succeeds, what do we get then? I'm typing here, so if you want to start typing, you just interrupt me. So this is just my notation, how I write this thing. So if it succeeds, it returns, we get the t value and the t position.
Yes.
Okay, we needed a t value to produce a parser u, and we have that here now. So, okay, then we can do it this way. I'm doing this pattern matching again inline because that's the way I like to do it. And this is a parser of u. So in order to complete everything,
we need to run it, yeah, against S and TI, yeah.
So now here is the position that is advanced. We advance the position. So you see, here's the, sorry, I need to mark again. Here's the initial position.
And TI is the advanced position.
And that's what we use to run the parser U. Now, this will enable us to start putting parsers together. And it might not be obvious, but this will do it. And it will also enable us another really cool thing, which I don't know if you've ever done before, but I think you could be interested in that. Yes, it could be all much more verbose. So
yes, maybe that's what we should do. Maybe we should make the variables. Yeah.
T value and I don't know, t position, t value, t position, u parser, t position, something like that.
So basically, we're using a function to define a new parser, aren't we here?
Yeah. We are yes, and also this is sometimes mind blowing a little bit with function programming. I sometimes forget that, but these things doesn't produce values. We are
producing parsers, isn't it? Yeah.
Yeah, we're producing functions because a parser is a function. So we take a function in here, we take another function in here, and we produce another function. So it's just functions on functions on functions. We don't really have values yet here.
Yeah.
But in order to see what this does, we can now start executing it. So I will write this as well, if you don't mind.
No, that's fine.
So we can clean this up. We understand these things now. So what we want to do now is we want to consume 2 characters, not a single character.
Right.
And the way we can do it is that we use pbind, and pbind takes a function, and here we get the character, and this function here is no, sorry, my bad. And I think I need another parenthesis. I think this is good. I'm gonna break the parser out, if that's okay by you.
Yep.
So I'm just gonna break it out in its own variable. So what this means is run this parser first, then run this parser and return that as a result. So if this thing here works out, what we will see is not H, but we see E.
Okay.
So just think like this, that pbind is a way to sort of bind these things together.
Okay, so it's like gluing 2 functions together.
Yes. So let's run this thing if you want to do it and see if I lied.
So what I expect to see would be H and E, would it then?
Well, that's what you expect to see. I
see.
expect to see an E.
An E, okay, so we got to second position, okay, and I has incremented to 2.
Yes.
That's good, okay.
So why didn't we get? But you expected 2 characters, right?
Yeah, I wondered if the P char would give us the H, and then
yes.
yeah.
But the reason that doesn't work for us is because this is the first character. The C here is the first character we get.
Yeah.
But we don't do anything with that. We just throw that value away.
Oh, okay.
So now is the time we're going to use our useless functions, p return.
And just return the value.
Yes, and I'm going to help you here again because
yeah,
this
do.
I'm going to call this f as in first, and I'm going to make a function here. So my bad again. So we take this character here and we bind it together with another function, and what we're going to return here, and here we get the second character. So here's the first character, here's the second character,
right?
And what we then do is we just say p return fs.
Okay.
So it seems strange and it seems hard, but this is a very flexible way to bind things together. So let's go through this again. We run this first character, a parser character. That's okay. Pbind lets us do is let us see what we parsed. So here we see the first character.
Yeah.
We are supposed to return a parser here that is going to parse the rest of the string. So we return a p character, but we want to look at the second character. So that's why we bind it together again here.
Okay.
So we get a chance to see this character here.
And p return is like the terminator. It says stops this and says that return the values you've got so far.
Yes. So we just package this together as a tuple and return that thing.
Mm. So now we should see H and E, shouldn't we?
Yes. If I done this correctly and we saved it.
Let's give it a go.
I think you need to save it.
Yeah, I saved it. Let's give it a go. And we do. H, E.
So it seems kind of useless, but this is a very powerful building block that we can use to start building very complex parsers from, or more complex parsers from. But I want to show you something which I thought was really cool in F# now. If you want to see that.
Oh yeah, absolutely.
So now I'm going to define a new function. Let me just type this. I'm going to call this p combine. And what this parser will do is that it will run this parser first, ignore the result, and return the value of this thing here.
Okay.
And this is actually quite common this is quite useful pattern when it comes to parsers, because we might sort of say here, let's look for the plus sign. I don't know if you can see my screen, by the way. Okay, let's say it's useful because often in parsers you say, I'm expecting maybe a plus sign here,
okay,
but I don't care about the plus sign. But I'm expecting it there. So if it's not there, I want to fail, but I don't really care about it once it's there. So what we do then is you write a parser that look for the plus sign in tparser, but we just return the value of the uparser.
Okay.
It can be a little bit hard to understand, but it's actually very useful in some cases. And we can actually implement this in terms of pbind. And this is exactly what we did the first. In that, if you remember,
okay,
the first thing we done, we run the parser t here.
Yeah.
And we run it, and then we bind it together, and we then return this as a parser u.
This is a function which takes anything, discards it, and just returns the u. Yeah.
So, and if I copy paste this thing here, oh no, sorry, yeah. So let me just type it here. I'm just going to demonstrate it very quickly for you. you don't mind.
You carry on.
So now, I can't save. But the idea here is that run the first character on the bottom here, combine it with this character, and this will mean throw away this result and just return this result. Okay. So if you run this thing, see what happens. I'm expecting an E.
Yeah, I can see this. It can be an E.
Yeah.
And that's what we get.
Cool. Now we're going to do the really cool thing here, I think, which I think you appreciate, because this was just semi-cool. We're going to define what's in F# is called a computation expression.
Oh, okay. So we're getting quite advanced here then.
Yeah, but you will see it's not that advanced, because we have defined all the building blocks that we need. So a computation expression in F# is saying we are implementing a class that has certain methods. And I'm just going to call this parser builder type, like this. Sorry if I...
Okay.
And this is just a pattern. This is something you learn. This is just something like learning about the strategy pattern or the proxy pattern. This is just a pattern. This
okay.
Is not, you cannot really... You have to read the documentation, but you learn it after a while. You know, this is just the way it works. So I'm going to define a member called bind, and this has two arguments, t and uf. And what I'm going to do is I'm going to call pbind using t in this order.
So
the arguments are split.
So let's just clear up the uf and thing. So uf is a function which is it's something that's going to return a parser of type U, yeah?
Yeah. It takes the result of the first parser,
yeah,
and returns a parser of U.
Yeah.
This, I'm going to write a comment, enables let bang. So you know about this let bang and do bang and these things, right?
I think I remember them. Could you just remind us what they are?
So I think you're quite used to this thing here, right? You write something like this.
Let's just scroll up a bit.
Yeah, sorry. My bad. I didn't think about that.
Yeah.
That bang, read string, async. So
that's like an await, is it?
Sorry?
Is it like an await? So you is that what it is? What's let bang actually doing?
So when you write an async, let's say this async, right?
Mm-hmm.
Let bang here is essentially the same thing as await.
Await, yes, that's what I thought it was. Yeah. Exactly
right. But in F#, this is implemented using something called a computation expression builder.
Okay.
So async is implemented in this way. This way, but it's called maybe async builder.
Okay.
So in order to make this work, async has a method called xbind.
Okay, so the x is just representing the class, is it?
The x is just this pointer.
Yeah,
this is,
this, yeah, okay.
It's confusing to many developers.
Yeah, got that.
What I want to define here is a parser, pchar, that allows us to sort of build parsers using this computation expression builder.
Right.
Because some people think that it's more readable. I'm not disagreeing with that. So I think that's pretty cool to enable that feature. Does that make sense?
Yes, I'm following you so far.
Yeah, very good. So then I'm just going to implement all the other methods. Like I said, this is, and you will notice that my names are not randomly picked here before.
No, you pick your names, yes.
P combine, UT, and X. So, and this enables do bang. And now I want to define a method called return b.
Yeah. So,
which is this.
So is this the dreaded monad you're building here?
No, it's not really. But this thing here plus this thing here means that a parser is of the monad type class.
Right.
So you could say that this is a parser implements the monad interface in some sense.
So I thought I recognised the bind, combine, return as being the kind of the signature or the components that required for a monad. So
yes, it's I'm not talking so much. But it is. But monad is a very powerful pattern to combine functions together.
Yeah.
And this function, even though it's looks very complex, it is very flexible, and we can implement a lot of other useful methods using bind. So that is why monads are so powerful, because it's a way to sort of support functional composition.
So Rambling Geek, so we're doing live share here, so that's why we can't actually see Martin's screen. We just see my screen, but he's typing into my Visual Studio. That's right. So if there's any kind of confusion with what's going on.
So I'm just implementing this thing for you.
The little blue flag is Martin's position in my file when he's typing, so yeah.
So now we have implemented a few methods here.
Right.
So the first bind is it allows us to write let bang. Combine will allow us to do bang. Return will allow us to type return, and return from is the return bang, and 0 allows us to write if then with no else.
Okay.
So you remember this thing here.
Yeah, it starts to look a bit complicated there, doesn't it? That.
It's, to many people, this is complicated. We can actually now rewrite it using the computation expression builder.
Okay.
And that could seem more simple to many people.
Right.
So I need to do another thing, I realize. Sorry. So now we're done. Oh, sorry, my mistake. Now we're done defining a computation expression builder. So I think it's pretty cool in F#. We talk about these computation expression builders as they are very complex, but they actually is just a class that implements certain methods that needs to have certain signatures.
So it's basically interface, isn't it?
Yes. And then we define this parser of the parse builder, and this will enable us now. And now I will let you write some code.
Okay.
So you don't get too bored here. But I'm just going to help you get started. Oh, what happened?
I'm just bringing you back onto the screen there.
Yeah. Return 0. Let's run this parser.
Okay.
Let's see if you build this and run this. I'm expecting to see a 0 now. Yeah.
Yep, 0, yeah.
So now, using let bang, let's recreate the first parser there that we thought were quite complex. Okay. So what you now can write in this parser brackets.
Yeah. Do I need to replace return?
Yes,
yeah.
You use let bang.
Yeah.
And you bind. Let's call this first, whatever. You can call it whatever you want. Equals p sharp.
Okay.
And new line.
Oops. Yep. Okay.
Oh, sorry. And then you type let bang again.
Yep.
Second equals p char. So we run the first parser. We capture the result. The first is a character, And what we return now is return first comma second.
Okay, so yeah, so I can get that. By running pchar, we get the first character and advance our pointer in the string by 1, and then second we're just doing exactly the same thing again.
Yeah.
Get the second character and advance the pointer.
And what's cool here, and this is another thing which I thought was amazing, this thing here, because when I wrote this parser, this SVD parser in C++ many years ago, I constantly have to pass this state around, this integer, this string.
Yeah.
And this is happening, but it's invisible.
It's all encapsulated inside pchar, isn't it?
Yes, and the bind operation.
Yeah.
If it's done this correctly, so let's run this parser and see what happens. Maybe I'm, just imagining things here.
There we go. So that's an awful lot. That's an awful lot simpler than that. But getting there means we have to write some functions which basically enable us to write this pattern. And some of those functions, as you say, when on the face of it, especially things like this, don't seem to make a lot of sense. But absolutely yes. So yeah, okay. So we haven't utilised pfail yet, I noticed, but.
No. But I'm thinking we're going to do that now.
Okay.
But if you look at this parser thing here, right? And just for fun, we can parse the third character to see that works, right? So I mean, that obviously should work, but
let's see it work, yeah.
And then you append it here, and we run it, and then we should see hell with a single L.
We do, yeah. Yeah.
Cool. So what actually happens behind the scenes, which you don't see here, is actually that F# compiler is rewriting this thing here. To what you said was complicated above on line 50.
So it's rebuilding this. This is like syntactic sugar almost, and it's basically going to do this anyway in the back.
I think this is called monad transformers. I don't really remember. It's called something. This special compilation step that it's transforming this code into what you see above.
Right.
But we don't care about that so much. We just accept it. Now, using this thing, let's do this fail parser, which is very useful. So now I'm going to make an analogy to a regular expression. So in regular expression, you have these character classes like /d,
yes,
/s. We want to have that as well. So let's define a digit parser that only accepts digits.
Okay.
And what you do is you scroll upwards then, and under p combine, perhaps you type p digit, let p digit, and equals perhaps, and then you type this parser bracket thing on a new line.
Yeah.
This thing. It's brilliant. Brilliant.
I don't know what's doing that.
Yeah. But that, I'm not so easily angered person, but when that happens 3 times in a row, I'm worried for my blood pressure.
Yeah. This is the IDE trying to be helpful in air quotes, isn't it?
Yeah, I'm like, yeah, that's really, people sometimes wonder why I shout at the screen at work. I don't really do, but I get frustrated. You need to do a type of brackets, curly brackets.
Curly brackets, okay.
And then you make a new line here. So, how to do this? Well, what we do is we're gonna read the character like let bang.
That was pchar, wasn't it?
Yeah, and you call it C or a char or I don't know. You're gonna write it something. C equal pchar.
Yep.
And then now let's see if I can remember this thing. You type an if statement. If char, so we're gonna use big char, big C is digit, and you pass the character to its digit.
Don't need brackets. Yeah, char.
Nope.
That's one of the hard habits to get out of, putting round brackets.
And then we return the character.
Then just char, yeah.
Return.
Return.
We have to use return.
Okay, we're in the class. Okay, yeah.
Oh yeah, no. Okay, let's see how this thing works out. Okay, let's see now. I'm a little bit uncertain about this thing. Okay, but let's see. And then you go else. And then you type return bang. fail. Let's see if this compiles. I haven't tried this, so you have to type the unit value, the parentheses.
Yeah. So that's where it kind of catches me out with the brackets. Okay, so we've got a.
What does it say here?
The value of or constructor parser is not defined.
Ah, okay. No, this is very simple. I help you. Is that okay?
Yep.
It's simpler than you think.
Move the movie down. Yeah.
And this is because F# requires things to be declared in order, which I think is a feature, but this is something that we can trigger a religious war.
Well, it's just when you're in F#. I mean, when you're in C#, he doesn't care. So that's one of the things you have to get used to.
Yeah, I without going into too much detail, I actually think this is a very nice thing when I come into a complex F# project, because this is also applied on the files in F# projects. That means that the files on the bottom are the files that use everything
above it. Yes, yeah.
And the files on top uses nothing below it.
Yeah.
And that is actually, that for me makes it simpler to go into a project and understand the dependencies.
It also means you've got your building blocks at the beginning, so they're not scattered randomly throughout the whim of the developer. You can have private methods and public methods all scattered around inside your C# files. Here we're making sure that it's logical order. Yeah,
and I like that, but there are also several drawbacks.
Yeah.
So let's see, can we run this parser now?
I'm sure we can run it, yeah. So let's see. So it should.
But okay, let's talk about this parser, what we do. And maybe we should do that quickly before we run off. So let's see if I can scroll down to it. So, okay, I have the P digit on my screen. So using let bang char, pchar, we have a character, which can be anything, right?
Yeah.
But we only want to limit this to digits. So we do this, if a character is a digit, well, then we return this character to as a result. But if it's not, then we're going to fail, and I'm going to use the fail parser. But since this is a parser, we have to use the return bang.
Right.
And if we succeed with this thing will only consume digits and not letters. So let's see if this thing works.
So we need to actually run it somewhere, don't we? So do we need to set P to be P digit?
Yeah, for instance.
Or put P digit here?
You can put P digit here, yes. If we've done this correctly.
So this should return us none at this stage because we've got a H as the first character, haven't we? Okay, well, let's see what it does.
None.
There, returns none, yeah.
And if you put in a digit in the first character, what happens then?
So we should get a 7. We do.
And 7. Yeah, brilliant. We did a digit parser. Now, we're gonna need a parser for letters, and we're gonna need a parser for white space. So we can define them as well. So if you scroll up again to the P digit, so what we can do now, we're gonna make this more generic. This function, we're gonna reuse this function to create other parsers like this.
Okay.
And what we're gonna call this function is pSatisfy. So if you change the name to pSatisfy from P digit, and it's going to take a function. You can call this function satisfy or whatever. Satisfy, but it's
You know my typing.
I guess you're nervous now.
Yeah, there we are. Satisfy, there we go. Got there in the end. There's the S going, there we are. Oops, that's a D, there's an S. There.
Perfect. So what I'm going to help you a little bit here.
Yeah.
This is a function that takes a character and returns bool. And it returns a parser of char. Now, how do we use satisfy? It's very simple. Instead of using char is digit, we just call satisfy function on the character.
Down here?
Yes. The small, yeah. But not char. We remove the char. Yeah. Now we have a pattern for this thing here. And once again, I want to point out that what we're doing always is that we are reusing parsers that exist into writing more and more complex parsers. So we are kind of building, in my mind, molecules of parsers.
Yeah.
Where we start with something very simple. You remember the p-char parser? Extremely simple.
Yeah.
Now we have something more complex. And we have combined this thing using different rules. So let's define the p-digit parser again under the p-satisfy. And this time, now it's very, very simple to do that because we just say that p-digit is equal to p-satisfy. Char is digit.
So that's just giving. All we're doing is passing in there the condition that we want.
Yes.
To satisfy. So that's that's amazing. So yeah.
And this is conceptually identical
to what we
or equivalent or whatever to /d in regexp.
Yeah.
So let's define a letter as well. So then we say the p letter is p satisfy.
Of course, in reality, what we'd do is we'd hide all this stuff, all of this in helper file, and we wouldn't ever need to look at it again because we've already defined all this. Yeah, this is so char is letter.
Yes. And so on. We can define a white space, and we can define more and more. But we can stop with this for now. We can just try this p letter parser to see that it works. So now it should fail, right?
Yeah.
So let's see if that will run. Yeah, cool.
Yeah.
And if we remove the 7, it should succeed if we've done this correctly.
There we go.
Yeah. So the next step, if maybe you have some questions, by the way, I'm just going forward here with my.
No, I can see. It's starting to gel. I guess one of the difficulties that I get is that I kind of understand it each step, but when we move on, we kind of take, okay, we've got that working, so we can move on to the next part, and then the earlier stages start to kind of fade a bit. But we started off really simply with a very simple definition here.
Yes.
And it all seems to kind of it's all kind of based upon this, isn't it? This is just a single character. Get me a single character or nothing at all.
Yes, exactly right. And we're going to use this thing to compose more and more complex things.
Yeah.
But this is the atom, maybe we can say. I sometimes call it atom. And then we use parsers like bind as sort of. It's not perfect, but it's molecule bindings. It's sort of bind these molecules together.
Yeah.
It's more. And if you think about spaghetti code, we all know that thing, right? It's basically that we bind functions together, but without a real structure. But I think the difference here is, yes, we're going to build complex molecules, which will be complex, but the binding operations are standardized, and they give a structure to the code.
Yes, it's always the same way of the bind or the combine are always the same, aren't they? There's no other ways of doing it. You just use the same function. The combine, which is made up of bind, which is made up of a parser, which is made up of these things. Yes.
So, and it's all building on itself. And sometimes we have to write new functions. And now is one case where we have to write a new function because I want to parse an integer now. So we have a digit parser. So conceptually now we can get into the position where we can parse an integer, if you know what I mean.
Yep.
But in order to parse a digit integer, we need to be able to read multiple digits. We don't know how many.
Correct. Yeah.
It can be 1. It can be 10. So on. So we're going to define a very cool function now, which well, at least I think is cool, which is comparable to the star operator in regular expression.
Okay.
So type /d star, we get 0 or more characters.
Yep.
And we're going to define that parser combinator that allows us to take any parser and repeat it 0 more times.
Wow. Okay.
And this is so I'm up under the combine.
Under combine, yeah.
So I'm going to write the signature here.
Yeah.
And this thing takes a parser of t, and the type of this parser is going to be t-list. So it takes a parser that produces a single value and makes it into a parser that produces many values.
Okay.
Does that make sense?
Yep.
And now this is a little bit of low-level parser, so now I'm going to do it again using this signature here. The way so this will involve a loop, and I'm just going to describe what this loop does in principle. The way we're going to do it is we're going to apply the parser t until it fails.
Okay.
And when it fails, and when this parser fails, we're going to say, okay, whatever the result is, we return this thing as the result.
It makes sense, yeah.
Yeah. In F#, for loops doesn't support a break, like in C#. So in C# we write the for loop for this, and then we break out.
Yeah.
But the F# doesn't support that. So what we do in F# is something called tail recursion.
Okay, I think I've heard of tail recursion, but let's see it. I'm sure I'll recognise it.
Yeah, you're probably recognize it. But I also want to describe for the viewers as well.
Absolutely, yes.
Whenever you need a loop in F# that breaks out, tail recursion is the answer. That is the way we do it.
So just so I know where we're going, is this the X and X's pattern?
So is this?
Well, you take the head of the list and then.
Yeah.
Is that the kind of concept?
We're actually going to do kind of the opposite.
Okay.
So I'm going to write this loop for you.
Yep, if you would.
And this is a recursive function. So we say let rec loop, and we're going to aggregate a list. So we're going to aggregate values. And what's cool about tail recursion is that it often allows us to avoid mutable states. So we're going to aggregate a list, and let's see what we're going to call this thing. CPOS, or maybe call it current position. Let's call it like that.
Yeah, it's probably has to be a bit verbose so that we can all kind of follow what. Yeah, so Surly Dev just says, "Oh God, recursion."
Yeah, but that's how we do it. That's what we do in F#.
Yeah,
we love recursion. Well, tail recursion is very, very good in F# because what happens under the hood, which is very, very important to know, is F# compiler relies on something called tail recursion optimizations. And that actually means that even though we write recursion, this is going to be implemented as a loop. So it's going to be very efficient as well.
Yeah.
And I'm going to explain what tail recursion is while I'm writing this thing here. So what we're going to do now is we're going to run the parser t on the string s we get as input, and we're going to use the current position that we get as here, right? So I run the parser T using the string S.
And the current position, yeah.
The current position. And if this thing fails, you know, that we expect it to fail at some point.
Yeah, we finished, haven't we, at that point?
Yeah, then we finished, and we're going to return VS current position.
Yeah.
Does that make sense?
It does, yes.
Yeah. I'm going to add a little bit here, because when we're aggregating a list, because a list is a stack, so because it's a stack, we are the last value is going to be first in the list.
Okay, so it's reversed.
Yeah, so I'm going to reverse this as well. But that's basically it. We no longer have positions, and then we have some value, T value.
We just want to keep going at this point, don't we?
Yeah. So okay, we succeeded. And what we do then? Now we do the tail recursive loop. Okay, we have a value, we have a new position. Let's call ourselves T value, T VS, T pos.
Yeah. So that's the I think that's the syntax I remember seeing.
Yeah. So what we do, we take this value here and we add it to the value VS here. So we're aggregating the list, and then we use the T pos as the new current position. And the reason this is called tail recursion is that we don't look at this happen at the tail. We're not looking at this result, and this will enable the compiler to eliminate the loop, this recursion, and make it into a loop. Because if we was looking at the result, it needs to be implemented as a recursion.
Yeah. So just so everyone's clear that this basically we pulled out T value, and we're gluing it back on. That's right. We're gluing it back on the onto the is it the head of the or the yeah.
We're adding it to the head.
To the head of the list. Yeah.
Yeah.
Yeah. And then we're going to process that again.
We're going to invoke the loop, and it's very, very simple, like that.
Yeah.
And this is the Mac thing. So we're done here, actually, I think. So do we understand this thing? So we defined a tail recursion loop. We're aggregating a list here, the VS. We have the current position. We try to apply the parser, and as long as that thing succeeds, we append the value on the aggregated values, and we update the position and go again. Yeah. When it fails, we take whatever state we have, we reverse it, because when we aggregate a list, it gets aggregated in reverse order. And we say, this is the current position. This is how far we got. So let's try this thing now. So what you can do now is you can, if you go down in the example below.
I just want to make it clear to everyone that this is defining a new function.
Oh yeah.
So the loop is a function here, and this is where we actually call the function.
Yeah.
So this is the definition of what the loop does, and then we call the loop on the so it's the empty list, because that's what's going in. We're starting off with an empty list, and we're passing in the current position that we're going to start, and then we're going to build up our value, our integer value, or whatever it's going to be, is going to build up in this list here, and then up the output.
So let's modify here, and you know, C# developers these days, we have the local functions, right?
Yeah.
So we're not scared about these local functions.
Exactly what that is. That's like a local function which we have to, in this case, define before we use it. In C#, we could define it afterwards, but it's just exactly what that is. Yeah.
Brandon talked about that the preferred path is defined after.
Yeah.
And it's a luxury we have in C#, but not in F#.
Yeah.
So if you go down to the bottom and you have a P run here.
Yeah.
And then you say parentheses around the P letter.
Okay. Yeah.
And then you say P many.
Inside or outside?
Before P letter, but inside the parentheses. Yeah. This is just how F# works with function applications. We have to add these parentheses here.
Okay.
And then we run this and hope for the best.
Okay, so we kind of guess we should get as far as the F. I guess I don't know if it's going to count.
Yeah, I'm not sure about that.
Let's see what happens. Let's see what happens. Yeah. So that's we're going to forecast it's going to get as far as the F.
Or a massive crash because I didn't implement it. No, a space is not a letter.
So okay, space is not a letter. Actually, we forgot about that. So but it got hello out of there.
Yeah.
That's pretty impressive. So
Well, we're getting somewhere now.
absolutely, yeah.
Let's try the digit thing here.
Okay. P digit. We should get nothing back from this because there aren't any digits.
Yes, there should be. We should get an empty, but it shouldn't fail here.
Yeah, it should get an empty list, which we do get an empty list, which is better than getting null.
Yeah, and then we add a few numbers here and we see what happens.
We put 42 in there.
42, obviously 42.
42.
Or as
It's got to be that.
I would say 4 as a random number.
And there we are, 4 and 2.
And it's in the right order.
Yep.
Brilliant. So now I'm gonna let you to. So this is conceptually similar to /d star.
Yeah.
This is what we've written, but I want to write /d plus now. Bye bye, Rambling Geek.
See you, Rambling Geek. Take care.
You did write some recursive functions in VBScript a couple months ago. In VBScript in 2019. I'm happy to hear that. So let's implement /d plus. And now I'm going to let you do it.
Okay, so /d plus does what exactly?
So /d plus fails if there's no digits.
Okay.
So because here we succeed if there nothing matches. So we want to have something that fails if there are no matches.
Okay.
And yes, so and I want to use the parser. Let you use this parser helper thing with it. So you have to write this below the parser.
Okay.
Because this is quite simple when you do it this way. So, and the way this is usually called is p many 1.
P many 1.
Yes. And you take a parser t as an input. And this is equal to this parser bracket thing we typed before, so you have to type a new line. Because now we don't have to do, we have a low-level thing, and we're going to reuse this low-level thing to write using high-level combinators. So you have to write the brackets.
Yeah. So sorry, the brackets around parser, is it?
I'm going to help you.
Yeah.
So explain what I mean.
Oh, okay, right. Sorry, curly brace is fine. Yeah.
Yeah. Actually, so, okay. So what is the strategy to implement this thing here now for us? It's quite simple. We're going to apply this parser once using let bang, and then we are going to run p many on this parser to get the rest of the values, and then we're going to concatenate them together.
Okay.
So you read the first value.
Like that,
no,
yeah.
Not pchar, because this is not a character parser necessarily.
Okay.
So you're going to run, you type the equal sign in the beginning too. So let's remove that thing here. So let's call this value or whatever you want to call it. Value is probably, not none. Christ.
Yeah, it's our ID being helpful. There we are.
Yeah, equals.
Yeah.
T.
Okay.
And then that is the first value. And if this thing fails, the whole parser will fail. And then you type, we can call this head, because this is what it is.
What value? Head?
Yeah, change to head.
Okay.
And then you change this thing, and it says let bang. And now we're going to read the rest, which we can call the tail then. Equal many t.
P many t. P many of t. Okay.
And then what you return is return head colon. So you append head to tail.
Is that a return bang? Or just return?
No, return bang.
Yeah. Okay.
So does that make sense to you?
So what we've done, we've pulled the first character off.
Yes.
We've processed. So there's got to be one, hasn't there? So what it's saying is that the parser, whatever parser we pass into here, we'll pull the first character off.
Yeah.
And if we pass a p digit parser in,
yeah,
it'll pull the first character off. If that's not one, it's going to fail.
Yes.
Otherwise, it'll at least produce one digit.
Yes.
And then it'll carry on and see if it's got any more digits and produce those as well.
Yeah.
And then it'll glue them together.
Yes. And I want to point out that the T parser here is not necessarily a character parser. It can be a parser that can parse anything.
Yes. That's the key, isn't it? Yeah.
Generic parser. It's not just character. But now we can use p-many1 to parse the many digits, at least one. So if you change from p-many to p1, let's see what happens. If we run this thing.
So we should get 42 again.
Yes, and then we remove these things, and we're expecting this thing here now to fail.
So we should get none, I guess. No, null at this stage. That's what my guess would be. Rather than getting an empty list. And we do get null.
Cool.
So that's worked, yes.
So, that's pretty cool. So, but we want obviously not to have a list of characters. We want to have an integer.
Yeah.
That's what we want to have. And in order to get that to work, what we need to define is a function which is very, very useful, which we can call pmap, for instance. This is the mapping function that maps from one value into another kind of value.
Okay, so it's basically changing a type, is it?
Yes. Okay. And this is called map. In C#, this is called select.
Right, yes, okay. So this is where we get the kind of crossover where we think we're writing in C#. We kind of think we're in the object-oriented world, but actually when we're using link, we've actually crossed into the functional world, haven't we?
It's actually kind of the same thing with a different syntax.
Mm.
And we can actually define this thing. If you want to continue using this parser, we can actually define pmap here below pmany. And this will take a mapping function. We can call it mapping or whatever, or map. It doesn't matter.
Mm-hmm.
And it takes a parser t, and it equals to this parser curly brackets, like the previous line.
Yeah.
And then what you say is you execute the parser t using let bang.
That was annoying, wasn't it? It didn't do it second time, luckily.
Something like this.
Okay, value is okay.
Yeah, and then you return the value v that you passed through the mapping function.
Return v, yeah.
So you have to run mapping function on top of this thing.
Oh, okay, mapping, yeah.
Yeah.
So that's what's going to do the conversion. Okay.
Yeah. On value v, not parser.
The v, yes. The value that came back out the parser.
Cool.
Yep.
Very, very cool. So this is actually this is a very common and extremely useful function in many ways. So in order to define our integer parser, we're going to define a helper function here. I think is probably good. So if you take the line below here, you can define a helper person. So the purpose of this helper function is to take a list of characters and transform that into an integer.
Right.
And what you would do in C#, right, is that you will write a for loop that reads the first character and add that to a state, and then read the second character and add that to the state, but you multiply the state by 10.
By 10, yeah.
And so on and so forth. but we're going to do this using the fold function, because that's how we in Airshop you often do these kind of things. So this is a folding operation.
So folding, from what I seem to remember, is like looping through a list, but applying some function at each step. Okay.
Yes. And you're aggregating a step.
Yeah. An aggregation. Yes, it's an aggregating function, isn't it? Yeah. So yes, this is like the aggregate
exactly.
In LINQ, isn't it?
Yes. And fold might seem like a strange name, but the way I interpret this thing is that you're reading a long list of elements and you kind of fold it together using some kind of operation, so you get a single element out of it.
I think the way that I'll just hold a piece of paper up here that someone described it as you're folding the list like this, and then so you're kind of collapsing the list down. You got a list here, and you're folding it, applying your function, and folding it. Yeah.
I think kind of or aggregate, like
Yeah.
But it's so. Let's what's going to call this function? Make int, perhaps we can call it something like that, right?
Yeah.
And as an input, it's going to take a value vs, which is a list.
Yeah.
And what we do with this vs value,
just to kind of, the reason why Mårten's suggesting vs, it's like v is a value, so this is vs is like values.
This is functional programming language.
Yeah.
And the type is equal. And we're going to take this vs value here and pipe it into the folding function, list fold. And what list fold requires us to give is a folding function, that is the aggregation function.
Yeah.
So that you can type a parenthesis now, and this takes fun, or maybe this is simpler. I actually like this often. I think this is often simpler to do this. So let's make a new line above this thing here, between, and you create a new function here that we call folder or whatever, and this takes a state. This takes two arguments. Before let's take a state. Egg is fine.
Yeah.
And then it takes a value, which is the character, so you can call it char or whatever.
Mm-hmm.
And this is equal. So what we're going to do now, egg is an integer, and we're going to multiply that by 10, because any previous state we're going to multiply by 10 before adding another digit. So we just multiply agr by 10.
Yeah.
And we take this plus, and we're going to make the character into an integer. And the way we do it, so this is a little bit confusing to me. So I will suggest that we change the name of car to ch as a shorthand.
Yeah. Okay.
Because there's also a function called car.
Yeah.
And we make this into an integer by saying int ch.
Yeah.
And then we take minus int and the character 0. Not the 0, but the character 0.
Character 0, like that.
Yeah, but this is a string, so you need a character.
Single quotes, yeah.
So does this thing make sense? We're multiplying and
minus, sorry, yeah. There we go.
Yeah. So we're multiplying this state by 10 to sort of, whatever it is, we have a new decimal number we need to add to it. So we just shift it up one step.
Yeah, absolutely, yeah.
And then we get the character, and when we cast it to using int, we get the ASCII value, the Unicode value, right?
Yeah. So we could probably make this a bit clearer by putting some brackets in. Perhaps.
That's why we subtract away the 0 value to get it to the decimal value.
Yeah.
And then, and then we use, in the list fold, we parse the folder function now as the first argument. You don't need the parentheses, by the way. And then we need to parse a Nisser state, which is 0.
Yeah, so this is exactly, I'm going to change this to folding func, I think, just to make it a bit clearer.
Yeah.
Okay. So it's exactly equivalent to an aggregate function in LINQ if people have done those kind of things in LINQ.
Yep. And now we're going to use this makeInt function to make a pint function that parses many digit characters into an actual integer. So then you say pint is equal to p many p digits and then you shove it, as Gareth says.
Yeah, I like that, shove, yeah.
And then you say pmap. So we're going to map it using the makeInt function, and hopefully we haven't screwed up.
So the elegance of this is quite astonishing in the end when you actually you start to think about what you're doing here. It's quite incredible. So what we're doing is we're saying we're going to do a p many using an integer parser. So we're going to get zero or more digits.
Sorry,
carry on.
p1.
P many 1, yeah. So we need at least 1.
Yep.
So we're assuming we're going to get a digit, at least 1 digit.
Yep.
Which is what this one, and then the result of that's going to be a list
of characters,
of characters, all of which should be numerals.
Yes.
And then we're going to put that into our mapping function. What that's going to do? That's going to transform. That's going to transform the characters into whatever using whatever function we pass in, and we're passing a make integer function.
Yes. And now we created a type safe integer parser, because if you compare this, now we gotten somewhere, right? If you compare this with how regular expression works, when you type /d+ in regular expression and you put that into a group, and then you extract this thing from the group,
it's going to fail, yeah.
It's still a string.
Yeah.
You still need to parse this string.
Yeah.
But here, you actually get an integer.
Yeah.
So we can try this thing now and see if we screwed up. It's entirely possible.
So if I put 42 there and I should just be able to do pint, shouldn't I, there?
Yes.
So, folks, we're hoping to get the actual number 42, not a list of characters.
That's what we're hoping for.
So keep your fingers crossed, everybody, who's managed to stay with us for this mind-bending trip. There we are, 42. Look, 42, and we're in the second position. So we're now, our pointer's on the H, but we've stopped at the 42.
Yeah. So we defined now a parser int. The type of the pint. I don't know if you can see it very simply in your if you can hover over it or whatever. The pint parser.
Yes, it's a parser of ints. Yeah.
Yeah. So
it's worked that out for itself, hasn't it? Really, it's worked out that the result of that is simply an int parser.
Yeah. Now this is type safe.
Yeah. So you can't do anything else. Yeah, that's amazing.
Yeah. And so this is one of the benefits. I'm not sure how far we're going to get, but this is one of the benefits of this kind of parsers, that we actually get out the actual type. When it succeeds, we get the actual thing we're looking for.
Yeah.
We don't get the bunch of strings that we have to, we do all that now in this way. So let's see if we can. I don't think we have time tonight, but let's see if we can define a parser that at least can parse this expression we see above, 1 + 2.
Yeah.
Even if it's kind of stupid. There are ways to make it good, right? But let's see if we get there. And it's not going to be perfect, but then we're going to define a very useful parser, which is called often pskipchar. And what this is going to do is just going to read a character and make sure that the character we're reading is what we expect it to be.
Okay.
So this is going to take an argument which we can call ch or whatever.
Yeah.
And this is equal, and now you can type this parser thing here. This is very similar to the psatisfy parser, by the way. So I don't know if you want to cut and paste that thing or whatever.
We'll type it in. Okay, so it's going to be B satisfies up here, so we're going to take the first character, are we, again?
Yes.
Let's actually grab the code, shall we?
Yeah. It's not completely identical, but it's very, very similar.
Yeah. And F sharp, remember, is depends on your indenting. Okay.
So, but the difference here is we're going to compare that the char we read is equal to ch. So we just type ch equals char. And what we're going to do here, because in this case, we know that the character will always, when it succeeds, it's always going to be this character. So we don't have to return these characters. We actually just going to return a unit here instead of.
Do we return unit just by using the word unit?
No,
just the open close brackets. Yeah.
Yeah.
Oops.
That's the unit value.
Yeah. That's unit is basically. I don't want to misrepresent what unit is. It's basically void.
Oh boy.
Yeah, it's not really void, but it's a value, isn't it? It's a value which, like, it's hard to describe, but you kind of think it as being in the C# world, you're returning nothing, but actually void is a value. And unit is that value in this. You have to excuse my very crude way of putting that, but maybe you could put it in a more eloquent way.
I will try to put it in a way. You have void, and void is a type that has no values.
Yeah.
And you have booleans, and what is that?
It's a type with two values, yeah.
Yes. And unit is kind of the middle between that. A type that only has one value.
Right. And that value is unit.
Yeah.
Yeah.
And because there is one value, this value cannot carry any information because it's always one.
Yeah.
A single value. Because it's always the same value, there is no information.
Yeah. It's no particular value at all. It's that one value. We don't know exactly what the value is, but it's always that value, and it's useless to us in that respect. Yeah.
But in F# we often use this to indicate that we have a function that have side effects, or that have a function that accepts no input.
So something interesting in F# is that functions always return a value. So there is no concept of a void, is there? I was very crude when I said it was like a void. There's actually no concept of a method or function returning nothing at all. It always returns something.
In a functional way, a void function makes no sense.
Yeah.
A void function is a function that it can never return because there is nothing to return. A function in a functional manner always return a value.
So if we just return to kind of mathematical roots of functional programming, a function is defined, I think in maths, as it maps from a domain to a codomain. So what we're saying here is any value we pass into this function, if it returned unit, you could pass any value into it, but it always mapped to a codomain which is exactly one value.
And this is a personal, what do you say, itch that is scratching here. So I'm just going to motivate why this is such a good idea. So let me take a 2-minute diversion.
Sure, yeah, absolutely.
We're going to talk a little bit C# now. So I scroll to the bottom, so I don't know if you can do that as well.
I'll do it, yeah. There you are.
Yeah. So in C# we have something called func, right?
Yeah.
Func, I'm just going to type it here, like func int x. So x, what is that? Well, this is a function that, given no input, returns an integer. Func int x is a function that, given an int, returns an int.
Yeah.
Now, what do we do when we don't want to return anything? When we have the thing that we shouldn't return any value? What do I type here? Do I type void? No, that doesn't work. Because void, there is no void value. So func void makes no sense. So in C#, because of this thing, we have something called action.
Action, yeah.
Which is very much like func, except it returns void. Now, if we have unit, and the reason for that is func requires you to return a value. Now, let's imagine C# had unit instead of void. Func int unit makes perfect sense because this is a function that can return a unit value.
Yeah.
So the reason we have action and func in C# is because we have void, which doesn't make sense for func, but unit makes sense for func.
Yeah.
Another thing is this: task int is a task that returns an integer, right? Task string is something that returns string. But what about the task that returns nothing, void?
Yeah.
No, that makes no sense.
Yeah.
So then we have to use this thing here, so we have to have two cases. And there are many different places in C# and other things where we need two cases for things: void and no void.
Yeah.
In C# there is no need for that because we use unit for that. So that simplifies things a lot, in my opinion, and makes writing generic code much easier. And I'll stop now. But also
I find that kind of thing fascinating, Mårten. When you kind of you see two different languages that got a different root, really.
Yeah.
One of which is embedded in the simple idea that a function maps a value to another value, and then something that's just grown up, completely separate to that. And then those two paradigms collide when you start to merge the two concepts together. When you start bringing functional into object-oriented, then you start getting the nonsense cases, as you say.
And in my opinion, this void thing is, I will not say a leak abstraction, but we have these abstractions around the Turing machine, around assembly programming. And when you write assembly programs, it makes a lot of sense to call a function. What you do then is you jump to an address and you start executing in that address. And then a void function makes a lot of sense because you call that thing and it starts executing that thing. But if you think about functions like more mathematical, which is actually how we think a little bit more like in C# more and more these days, and certainly in function programming, jumping to an address and start executing makes no sense. We are actually applying a value to a function and we get the value out. So this is kind of a leak abstraction so that we are actually executing on a CPU that jumps to addresses.
Yeah.
So that's a personal scratch itch there. I'm sorry.
It's fine. It's interesting stuff.
Yeah. So I find a thing about this is at work we were talking about programming languages, and I said, well, Kotlin is not so great because it's and now I'm burning bridges now, but it has statements, and that is I draw the parallel between statements and void. And in the end, I wrapped it up by we have freedom of expressions, but not freedom of statements. Thus,
Yeah.
F# is superior. No, I'm not superior, but it's an itch. So where were we? Okay, we defined this p skip char.
Yeah.
And we now want to sort of, try to define a parser that can read an integer, a plus, and an integer, and maybe compute the value.
Yeah.
It's going to be kind of stupid. We want to do. We can see how this works out. So let's write this thing here on the bottom. Let's call this just under the skip char parser, perhaps.
Okay.
Let's call it p add or whatever. I don't know.
Okay.
And then we say, what is this? And you type a new line equals. And we make this into a parser of these curly brackets, right? And now what we want to do is that we're going to read the first value, right? The first integer.
So that's going to be let bang. Oops. I'm going to stop. I'm just following you. That's as you move around, I was moving around there. So it's char equals.
Or first. This is not a char.
First, yeah. It could be anything, couldn't it?
Or left or whatever.
Yeah. First is going to be p digit.
No, p int.
P int. That's right. Yeah. So we're assuming it's going to be an integer. Yeah.
And then we want to skip. The plus sign.
So
and what we do then, we do bang, because
do
we don't
bang.
care
Okay,
about this
yeah.
one. And then we say p skip char.
And then we need to put the. So we're going to assume that it's a plus sign, are we?
Yeah, we're just gonna make this. We're gonna hardcode this and not make it super fancy.
Okay.
There are ways to make this really good, but we're not gonna do that right now.
Okay, like that.
And then we read the second. And I suggest we return now the first plus the second, right?
Okay.
Okay. Yeah, so
Yep.
let's try the parser.
So we're going to p run.
Yeah.
And it's going to be p add.
Yep.
Plus 2, which is so this is our statement. This is what we want to pass. Okay, we've got spaces in this one, but we're
spaces for now.
We're going to ignore those.
Yeah.
And then we're going to pipe that result out into a printf. And we're going to just use the a, which is anything.
Yeah, and you forgot the n. Print
n, yeah. There we go.
Let's see what happens.
Okay, well, I've every confidence. Here we go then. So we get 3. There we go.
Yeah. Let's change the plus sign to a minus sign.
Okay.
That shouldn't work, right? That should fail.
So we should then stop at 1, I guess.
It fails completely.
It fails completely because it couldn't understand when we hit the skip plus. It had no idea what to do then.
So first succeeded.
Yeah.
But it failed on that thing.
Yeah.
So now we created a super simple. I mean, I'm not sure we're going to get that tonight. But what we created now is a very simple expression parser. And yes, you could create this in regular expression, no problem. But the benefit here is that we actually get out the actual value.
Yeah.
We don't get out something that we need to parse. We actually get out an actual value. And we can also do like a key. Let's make a key value parser, right? And make a new parser that can parse what we often have, like key values. And it's basically the same thing, right?
Yeah.
But instead, we're gonna go for this equal sign in between, right? Because that's very common. That we have a key and a value. Oh, and the key shouldn't be an int, but let's leave it at int as for now.
Okay.
And you have to indent it.
Yeah.
And then you return not plus, but you return this as a tuple or a pair, right?
First, second.
First, comma, second. And then we can see that if this thing works.
So 1 equals 2, like that.
Yeah, it doesn't really make sense for key value, but what the heck, right?
Yeah, absolutely, yeah. So we're now, we're kind of in the point where we could start perhaps we could pass ini files or whatever, couldn't we?
Yeah, we're certainly getting there. So what does it say when you do this thing?
Let's have a look. 1 and 2. So it's picked out the two sides of the key value pair. Yeah.
Yeah. Shall we try to make a string parser just for the fun of it?
Yeah, absolutely.
So we made a p-int parser. So we want to make a similar thing to make a string. And this is a little bit simpler. So I'm going to suggest we write this. Let's see now. I'm thinking a little bit now.
Okay, no problems.
So let's call this p string. something like that. Let p-string. And this takes a t-parser. And I'm going to suggest that if we give this type now, or char parser, we're going to give the t a type. So yes, but you need to put parentheses around it.
Oh, okay, right, yeah.
And we're going to require that this is a char parser, so it's a parser of char.
Like that, or parser.
Yes.
Okay.
And what this returns, colon, right, is a parser string. And this is equal to, and maybe we say p many 1. We require at least 1.
Yeah.
And you run the t parser, and you run this through t, and then we run this through the mapping. We shove it to map. Pmap.
Pmap, yeah. So we got to pipe it in, have we?
Yep.
To pmap.
And then you write the function here,
which is
parentheses fun. And then we get now. Oh yeah, thanks for that. Right.
Yeah. I'll fix it. Don't worry. I'll fix it good and proper.
My blood is starting to burn here. And you have a list. I don't want to call it CS. I would call it a character list, right? What you can call it, whatever.
Char list.
Yeah, sure. And then an arrow. So this is what we want to convert to a string.
Yeah.
So what we do first. Okay, this is a little bit memory wasteful, but never mind. We convert this to an array by take char list and shove it through to list to array. I think it is a method called. Small t.
To array, yeah.
And then we shove it to the string constructor with the capital S, I believe.
Yeah.
Okay. Because there's a constructor that takes a character string in strings.
Yeah.
So let's, instead of having when you do the key value parser, now you need to move this above your key value parser. Yeah. So let's instead say the key value, instead of reading an int first, actually reads a string. String, and you say, so you see p letter. Because you need.
Oh, yes, the first letter, yeah, p letter.
No, p string.
P string, p letter.
Yeah.
That because it's a letter parser, right? I'll get that, yeah.
Because then you can have flexibility to define what should the string be built up. Should it be letter or digit? Should be,
yeah.
You get flexibility here.
Yeah, absolutely, yeah.
Then we go down, and we instead of say 1, yeah, exactly right. Yes. Cool.
There we go.
Very, very cool.
It's very cool.
Now, I want to wrap this up to a little bit even more cooler thing, if that's okay by you.
Yeah, absolutely, yeah.
So let's parse multiple key values now.
Okay.
And how do we do that? Well, we have a key value parser. And I'm just going to suggest for the simplicity that we make a white space. Like you need to remember the P letter and you need to remember the P digits.
Yeah.
Let's make a P white space.
So we can just copy this. Is there a char is white space?
I think so.
Yeah, there is. There you go. How useful.
And now, so let's parse all key values we have that are separated by a white space.
Okay.
And I'm going to think a little bit how the definition needs to look here. Okay, yeah, I have it now. So let's make a parser that we call p key values, and then you make this into parser. This parser bracket thing, right?
So we're starting to get into kind of patterns of how we define these now, aren't we? It's becoming a lot easier to think about these things. Now we're not at the atomic level.
We are kind of a high level now.
We're bigger than molecules even. We're at kind of cellular level now, aren't we?
Yes. We're building molecules and more complex. So I'm going to suggest that we do the same thing, that we read the first key value using the key value parser above. You have an equal sign.
Oh. So P key value.
Yeah.
And that's going to be P letter, presumably.
Yes. P. Yeah. No, that's
fine. Just that. That's right.
Yes.
Yeah.
And now we want to have. So now we're gonna, do this in one line and see if you like it. So then you see, let's call it the let bang rest. We can do no. Let's do it. Let's do it a little bit more explicit. Let's define a local helper parser. So between p key values and p parser. If you go up there, and you make a line between key values and parser.
Yeah.
No, I was thinking. I'm going to show you here.
You show me where you want to go. Yeah. Oh, okay, right. Yeah.
Left helper. I don't know what you want to call it.
This naming is hard. Yes.
And you complete this like parser.
Oops.
Oh, I think
I'm on the wrong place. Yeah. I'll come down to there.
Yeah. And you need to go these curly brackets things.
Yeah.
And it jumps around. And what we're going to do now is we're going to do bang many one white space. So we're going to require at least one white space or more. What does it say? Okay, so it requires you. Okay, so this is a little bit unfortunate, but whatever. So you instead say let bang. There's a way to fix this, but you say let bang VS or whatever. Yeah. We're going to use this thing, but whatever. WS equals something.
Just WS.
Yeah, WS equal. Yeah. No. Sorry, I was wrong. I'm going to help you.
So you carry on, yeah.
It's simpler than you think.
Yeah. Oh, okay, right, yeah.
So this is the white space. And then we're going to return a key value. So you do return bang key value.
P key value.
Yeah, P key value. So what this parser does is that it looks for a white space. It has to be a white space. And then it tries to parse a key value after white space.
Okay.
And now, using this, you can, in the parser here, below, say let bang, rest, or tail, or whatever you want to call it, equal p many helper. And finally, we return first and tail concatenated together. So if we succeeded now, this should return a list of key values.
Separated by white space, so.
And it has to be numbers, right? So,
yeah.
Okay, let's see if this thing works. This will be interesting. We are on this, doing advanced stuff now. So then you say key values instead of
Yeah.
We need to change the parser from key value to key values.
Yeah.
And we'll see what happens.
So we're hoping for three key value pairs to come back.
Yeah.
And there we are. They're there.
Look at that. And the type here of key values, if you hover over it or whatever, so you can see the type.
Yes, it's a parser of string, a tuple of string and int, and comes back as a list of them.
Yes. So it's type safe.
Yeah.
And so you can now imagine that this was a file containing key values, and we could then sort of parse all these key values into a type safe structure. Once again, we could easily do this in regular expression, but we kind of implemented now regular expression using Parser framework.
Yeah.
So I'm thinking, this is up to you, but I'm thinking it's getting kind of late at my site.
Yes, it is. Yes, it's quite mind-bending stuff as well.
Brain burning. So I would like to suggest that this could be a good point to maybe cut off. What do you think about that?
I think that's probably a good point. Yes, I think everyone's probably just about burnt out on the kind of brain melting side of this. But I think we've got a really good flavour of where this can go, and maybe what we can do is in a couple of weeks' time come back to it and see if we can build on it. Because I think it would be good to take it somewhere where we've got something which actually is generically useful. Because this is we're kind of hinting at how powerful this technique is. A lot of this stuff here, these building blocks, we can pull out, can't we, into another file. So we haven't got a huge file. We start working with these high-level pieces.
Yeah, and we've done everything from scratch here, right?
Yeah, absolutely, yeah.
There's no frameworks or anything to help us. We've written everything. And another thing I want to point out, and this is maybe because I've done this a billion times, we haven't debugged this a single time.
No, we haven't, no.
We have run it, and it seemed to work.
Yeah.
And I'm not saying that is always the case, but when you have these well-defined combinators with these well-defined atoms, when you bind them together, they become kind of well-defined. So they are well-behaved. So things kind of behave sanely when you bind them together in this way. And sometimes you need to debug to understand, but often you are kind of writing it like, this should work, and it often kind of works.
So I guess it's because we're building up from such small building blocks, and those building blocks, as you say, you're defining how you combine them. This defines how to combine them.
Yes.
And that is really quite a low-level thing. You've not described that at a high level. That's only slightly above the actual kind of atomic parsers themselves.
Yeah.
Then everything you build on top of that is really on firm foundations, and so you can't combine them in a legal way.
There are ways to mess up this thing.
I'm sure there are, yeah.
But you do it quite a little bit less. And notice again, we define this atom char parser, and we never then looked at the string, except from here when we extracted a single character.
Yeah.
And from this single character now, we have built upon this thing to create a molecule kind of that can parse key value pairs. Sure, regular expression, we can do all that thing, but using this thing, we will be able to do much more.
Yeah.
And we're actually not that far away from being able to do like a full recursive expression parser that can support parentheses and different operators like plus, minus, multiplication, and with different precedence.
See, it's really interesting because the way I tackled expressions previously when I was looking at F# was obviously to use a simpler version of expressions, which was the reverse Polish expressions. And because that's easy, because that's basically pushing and popping things onto stacks. But this is actually true mathematical. You're actually parsing 1 plus 2 in the correct kind of. I mean, okay, we're not doing, as you say, we're not doing operator precedence, and we're not doing parentheses, but we've actually parsed a true mathematical expression, haven't we? 1 + 2.
Yeah. We basically, what we need in order to complete this thing, but I think this is going to take a little bit too long for tonight.
Yeah.
What we need to define something, a special kind of parser combinator, which is called the chaining parser combinator. We need to define a union parser combinator that allows us to sort of try this thing.
Yeah. See till it works. Yeah.
And we need to define a forwarding parser. But that's basically 3 more functions we need to be able to define to be able to parse an expression that could look. I'm going to write on top here now. So if you scroll. So if you had these 3 more expressions, we could write an expression that could parse. I'm trying to write right here. Sorry. A + 2 times 4 + z with the correct precedence and using variables.
Yeah.
So we have now the parsers, and we also get out the expression tree. We don't get out like a string or whatever. Like we get out the proper expression tree. So we are 3 functions away from this thing here, and they're not very complicated, but they're going to take another 2 hours to do. To explain. So that's going to be a little bit too late for me.
Right, yes, we're getting towards wanted to close off anyway, but that was really fantastic. So we hit our goal, which was to parse 1 + 2. We actually exceeded that
by parsing key value,
multiple key value pairs. So that's actually fantastic. So
and we get them out type in type safe manner, rather than what we usually do in regular expression, where we get them as strings that we still has to parse a little bit.
Yeah.
I was thinking if I could find a good example. There is this library called fparsec. Now, no, I don't think I will go into this, but I want to just type this out here for you, to something to look into if you want to. Now, what we haven't done here, we have no error.
I think we've lost your audio there, Mårten. Could you just make sure you've got your microphone on there? I think you're back.
Am I back?
You're back, yes.
Okay, good. So there's a framework in F# called fparsec. And it's a very, very good parser framework. And what we haven't done, I think I know now what it was. But what we haven't done here is really, when this fails, you have no idea where it failed and why it failed.
Mm-hmm.
And what's so cool about fparsec, it kind of looks the same, what we have done, kind of. And it's built up in the same way. But when this thing fails in fparsec, it will tell you it failed on line 3, column 4, and I was expecting a digit, but found a character.
Oh, right, okay.
And you get that error message for free. It will just be able to infer that from your parser definition that looks here. And I thought that was amazing. In addition, we haven't written this. This is not very performant, if I'm being honest, but fparsec is very good performance. So I wouldn't recommend anyone to use what we're doing, but this thing here enables us to understand how fparsec works.
Well, I think that's the ultimate value of this, is that, as you say, that there's people who have spent kind of probably years writing these libraries, but by doing it from scratch like this, it's the only way to really understand how to combine these things. I know what I'm going to be doing tomorrow is watching this video on demand back, because at each stage I pretty much understand everything you've done. But now we've got to the end of the stream, I'm kind of at this level.
Yeah.
The p-adds and the p-whatevers, and I need to go back, I think, and look at the look at the building blocks, how we got there, because that's really the interesting part of it is building up from these very tiny little definitions. Yes. The kind of arbitrary complexity you can get out of it is fascinating.
And I also want to point out what we started talking about a little bit in the beginning, that I think this is a little bit what makes functional framework design different from object-oriented framework design. Is here we start with in object-oriented, I think we start with the big picture.
Yeah.
What is the interface of my thing? And then we break it down. But with functional programming, it's almost like we start with the smallest thing. And we put a lot of effort in that. Because this is, whenever I write my own functional frameworks, what I reiterate is to find a good atom or a definition. And when I finally have that thing, all the functions, if it's good, all the other functions will come out kind of naturally. And then we build on top of that. I don't know if it makes sense.
It does. It makes absolute sense, because when we start learning mathematics at school, we start off with 1 plus 2, as you say. We start off with arithmetic, yep, which is very, very basic stuff. And then as you work your way through your school life, you're ending up you're doing integral calculus or whatever, and it's all based upon those foundations. It's why you have to go through the addition, multiplication, and that kind of learning, because each layer is adding more and more kind of complexity, but you're always going back to fundamental operations in mathematics. And this is basically the computer version of that, isn't it? Is you're building up. I mean, you can even you can define a function add, can't you? And then you could build all that up. You could start at even lower level than we are here.
Yeah, there is a language called lambda calculus, which I know very little about, which is fascinating to me, that language, because it was defined in 1930s.
Right.
And in that language, you can define natural numbers. As you say, you define them using basic building blocks. And what's mind-blowing is that, for me, and this comes back to a little bit what you say, is you have nothing in that language. But you start by building these atoms, and then you start writing them, combine them together. And all these operations like multiply and add, turns out they are like one-liners. Everything is super simple.
Yeah.
And it's just building upon some very cool foundations. But it is, the problem with functional programming, maybe I'm coming to, is if you don't, the way I try to understand functional frameworks is I try to understand, I'm going to mark this thing here now. The way I approach it is I try to understand the atom or the minimal block.
Yeah.
And if I understand that thing, I'm able to understand the framework. And maybe that's a little bit different from maybe object-oriented, but try to understand the big picture. But if I understand how the thing works, the smallest thing, then everything else for me makes sense.
So this definition you've got highlighted is absolutely key, isn't it? It's the first thing you started off with, is by saying, what is a parser? I asked you what a parser is, and you basically answered it by saying it's a type.
Yep. Which
has a generic type, okay, and then it basically takes a string and it produces a value which is either some type and a position or none, and that's basically it boils down to that. And that definition you've got highlighted, and I'll re-highlight it there,
yep,
is what we've all got to go away after the end of this stream and really kind of think about, because
yep,
that is the key to the whole thing. Everything else has been built up from that definition, and PCHAR is functional as well, is fundamental as well.
Either Sujin, yeah, and if you mess up this thing, all other function will suffer from that.
Yeah.
Everything will feel clunky. If you make it really good, it will come out good. So this is really where you put in your brain power in the beginning. But you can sometimes you cannot nail it the first time. So when I write a function framework, what I'm iterating over and over again is the basic definition.
Yeah.
Till I get it right.
And I guess you get kind of a sense that you've got it right, because the rest of it starts to flow more naturally. If you get it wrong, you say it becomes clunky, and then you start saying, "Oh, this is feeling difficult."
Yeah.
The rest of it flows. Okay, yeah.
So so I can give you more examples. So I think fascinating, but I think that's a difference, and I think that's maybe an interesting difference to you.
Yeah, I mean, it's good that we get exposed as developers to different ways of thinking, and there's so many people that you come across in the development world who are, JavaScript programmers or they're web programmers, and never get exposed to a different way, a completely different programming paradigm, and this is why I started watching kind of Gareth Hubble's streams, because he was looking at a different way of thinking, and it's completely mind-bending. It really is, for someone who's spent 35 years in procedural languages.
And you might think, perhaps like, Mårten, he knows the functional stuff, right? So he's never confused, right? But I can tell you, I had a big success this weekend when I was able to, for the first time, understand how something called van Laarhoven lenses works in Haskell.
Right.
That was a big step forward for me. So I'm confused like everybody else when I see something new, or when I see something that is more abstract than I'm used to. But when I get it, it's kind of, you look at this one-liner and like, how does this thing work? But when you get it, it's very rewarding, and then you understand everything.
Yeah.
Because when you understand this line here, the parser line, you understand everything about this framework, kind of.
Well, I think you know, say if you don't understand that first line, then you can't understand the rest of the framework. Yeah. I think you can kind of get your head around that, then you can start to pick your way through the rest of these lines that you've written here, and start to build up an understanding.
So when Gareth talked about this Chiron framework, and I helped him a little bit on that thing, right? So what I want to do when I looked at Chiron, so I recommended Chiron for Gareth, but I never really knew anything about it. I thought I heard it was cool, right? So I said, let's try. But then I thought I should help him out. So what I did, I looked at this definition of the Chiron core definition of what that is, and by understanding it, I could then describe it. But I had to understand that one line.
Yeah. And
that can take some time.
Yeah. Crimson Green, welcome to the stream. We're just kind of starting to wrap up now, but could you just tell us did you manage to do your speed run of Earthbound? I had to drop out of your stream earlier in the week. I think it was Sunday. So let me know if you managed to beat your personal best on Earthbound. So Martin, thank you very much for this this really fascinating stream that you've done a really fantastic job to take us so far through this concept of parsing. And I think what we need to do is arrange a future stream in a couple of weeks' time to come back and maybe try and finish this off.
I had a very good time to be here, so I'm very glad to be here, and not just trolling in the chat. And actually doing something to sort of help the community a little bit.
Yeah, and that's the kind of key to this, is that these streams, Codebase Alpha streams, and all the other kind of live coder streams exist to try and, they're not like an ego trip for us on this. We're trying to kind of, in our little way, help all the devs out there at every level, and also we're learning such a lot ourselves. So really, really appreciate the effort you put into this, Mårten, and thank you for joining me for this at this late hour. So so thank you very much for that. So what we'll do now is will
this be on YouTube?
Yeah, it will be on YouTube. Yes, it will be on YouTube in 24 hours time, maybe a bit earlier.
Because then I will share it with my teammates.
Yes, absolutely. Yes. So it'll be available on there. So I'll just post into chat my YouTube channel.
Mm-hmm.
So head over to YouTube. Please subscribe. It helps me out.
Can I see some Electric Elf? That's what I'm waiting for.
Oh yes, so Mårten has created some fantastic shaders for us on Codebase Alpha. So here's this is Electric Elf. This is one of one of the shaders we've got. Oh, I'm getting a.
No, it doesn't work. Oh, damn it.
Oh, I know why. I think we need to go to a different. So I'm just going to pop across to our. There we are. There's Electric Alf. He's not on our pair programming scene, unfortunately, but that's Electric Alf. So this is. I think. Do you want to describe what this actually is, Mårten? It's a shader, isn't it? It's wonderful. I've pressed my Steam Deck button so much that it's going on forever. But we've got another one, so this is going to probably destroy the stream now. Let's try a. There we've got Infinite Elves as well. So this is another shader which has got a mathematical set which is being represented by all these images. Same time, yeah. I think I've pressed Electric Elf so often that it's going to go on forever. But never mind. That's this one here. Right. It is very cool. I'm going to go back to pair programming because there we go.
Yeah, so I want to point out for the viewers, whoever cares, it's real time. It's happening.
Absolutely, that's all real time. So that's actually a website which is running now, and you can go to the website, and it's actually so every time I press that Stream Deck button for the hyperspace hype, it's actually a different slice of time. It's different every single time I press the button. With the Electric Elf, it's also different.
You're forcing your GPU to do some work, because it's really, I mean, if you think about the floating point number of calculations to do that, that's mind blowing.
Yeah, absolutely.
You know, because sorry, I'll get into some details, but you do 200 iterations per pixel, and you have a 4K screen, perhaps. That's a lot of pixels.
Yeah.
And then you do about 11 floating point operations per pixel. The number of floating point operations to do that, it's just mind-boggling, and you do it 60 frames per second.
Yeah, I think that's probably why that the hyperspace Alf one does degrade the quality of the stream while it's on, which is why it's not full screen.
Yeah.
Even at that size that we had it there, you do notice that I think I start to pixelate out of a bit. So it is incredible what you've done there. It's absolutely astounding. So I really appreciate that. So thank you very much.
I don't force myself onto the stream, but if you ever want to talk about how to make pixel shaders, that's something.
That's it's your bag, yes. Okay then, thank you very much, Mårten. Let's wrap the stream up then. So we're going to go and find someone to raid, I think. So Crimson Green, you said you died in a miserable and fantastic death in Earthbound, so you didn't manage to do your PB. I'm sorry about that. It was very interesting to watch your stream, so I hope you're going to stream again very soon. Okay, let's find someone to raid, shall we? If we can. So if anyone out there has got a preference who they'd like to go to, we've got Code Phobia and we've got Sawscoot. Let's go and should we raid Sawscoot? As he has raided us in the past, so let's go there. So thank you all you brave souls who've stuck with us through the stream. It's it's not a relaxing kind of chill stream like some streams you get. Today has been a real workout for our brains. So once again, I'd like to thank Phil Snable, Mårten for that exercise. And we're going to now close out by raiding Source Scoot. So do stay with us for that raid. So good night, everybody, and we'll see you on Wednesday when we're back on the AI chatbot to try and finish that project off, or at least move it slightly more towards the completion of that project. So thank you, everyone, and we'll see you soon.